the fundamental two models. To quickly, we are going to go through McCulloch-Pitts model. However, the more practical models start evolving from Perceptron model onwards. So shortly, you'll understand what is the reason. So what are all the limitations of the very first model, McCulloch-Pitts model, which happened in around 1943, very first model. They have demonstrated using logic gates. During that time, there was no sophisticated software, not even computers were not available at that time. They were able to demonstrate using a hardware circuitry, on and off. So they just demonstrated if with the binary input values, like there is off, both are off, both the signals are off, what is the response? If one signal is on, another signal is off, what is the response? Okay, either on, off. If both the signals are on, what is the output? So they try to demonstrate this using a hardware circuitry. That is why they have selected two logic, the two popular logic, AND logic and OR logic. We know X1, X2, Y. We have, these are the four combinations, right? Binary 0, 0, 0, 1, 1, 0, 1, 1. The AND logic, only if the two inputs are on, then only your output is on. Rest all other combination, your output is 0. So that is why you can notice the 0, 0, 0, 1 and 1, 0 belong to one class. And 1, 1 is the pattern. You just understand X1 and X2 are just a pattern or a features. This belongs to another class, 1. So typically this comes under the linearly separable problem. And of course, using a simple architecture, of course, it is a mathematical representation. Even I can say just a hardware wiring. Okay, the modern day neural network has two capabilities. One should be a physical structure. Number two, should have a logical reasoning, meaningful learning behavior. But 1943, it was a big breakthrough. During that time, it was a big breakthrough. Okay, some mathematical model they were able to represent. So during that time, since there was no such software computer development was there, those days this was one of the very big breakthrough, and people have celebrated this logic they demonstrated, McCulloch-Pitts model, which is considered as a mathematical equivalent to the biological computational aspects. Okay, just to quickly in 2 minutes, we'll try to match the biological process with the mathematical representation. In McCulloch-Pitts model, what they have demonstrated, it's a sum of products. Okay, sum of products of input. Your input is being scaled by W1, W2. It reaches a summing point. And McCulloch-Pitts model, there was no net concept. So sorry, there is no bias concept. Okay, the bias concept was introduced after nearly 10 years, I guess, by Rosenblatt. There is a scientist called Rosenblatt. So this scientist introduced the concept of bias. And what is the practical significance of bias? We'll understand when we discuss the advantage of Perceptron model over McCulloch-Pitts model. So before that, there was no bias. So basically, your equation goes like this: x1 w1 plus x2 w2. Just like your linear regressive equation, right? In your linear regression equation, the x1 beta 1 plus x2 beta 2 plus you have intercept term, but here there is no bias term. Later on, only bias term is introduced. So what we call this term in neural network, we call this term as a net value. Okay, this net is found to be a numerical quantity, continuous numerical quantity. Up to this, if I stop, you can treat a neural network model as a regressive, because your model can be able to map a combination of input to the output value. But the initial design was demonstrated for classification, not for the regressive. So the initial demonstration was demonstrated for the classification. So what they have done, so those time there was no sophisticated activation function like a sigmoid. Sigmoid was emerged little later on, around the 1950s and above. So that time, how they have demonstrated, whatever the continuous value they have got, okay, they fix a manual thresholding. Since they have demonstrated this using a hardware circuitry, okay, so the moment an output, because this net is found to be like a continuous output voltage, assume some millivolt, okay, the moment your output crosses certain millivolt or certain value, they say that, okay, they made it as on. If it is not crossing a particular threshold, they made it as off. This is how they demonstrated using a hard threshold. This is called as a hard threshold. Later on, Rosenblatt came and introduced a soft threshold, perceptron model. There we use the soft threshold. The soft threshold is same as our logistic function, in which already you're familiar with. Whatever this value, this continuous value we have got, this is being mapped onto this function. 1 divided by 1 plus e to the power of this net. Okay. Currently, we don't have a bias. After introducing the bias, okay, we are going to substitute the net value in this equation, so that your continuous value is mapped onto the probability score ranging 0 to 1. So this is an idea. So first, we'll see what are the drawbacks of the very first model, McCulloch-Pitts model, and how Rosenblatt overcome those drawbacks in his very first single layer perceptron model. Okay, before we see that, okay, let us have a quick understanding about a biological neuron. However, it's not significant when compared to our modern day practical approach. But however, after all, we are learning neural networks. At the end of the day, if someone asks you something related to biological neuron, you should be in a position to understand and answer it. So this is a structure of neuron. In our central nervous system, all the communication happens like a relay race, passing a baton. One neuron passing a baton. Pattern is what the signal. So our human brain is basically our brain, or in general central nervous system. Let me call it as a central nervous system, which includes the brain, spinal cord. So all the inputs we receive through 5 sensors, isn't it? All 5 sensors. So your inputs coming. So mathematically, what we call these inputs as input variable, x1, x2, x3, x4. You can call it as an input variables or features or attributes. So in the biological neuron, which is the input, you see a vision, your visual stimulus, auditory response, touch, smell, and taste. All these inputs constantly, our human brain is receiving the information constantly, right? It's being processed constantly, continuously. So all these informations are received by sensory neurons. Okay, it has a hand-like structure. You could see this is called as a dendrites. This is called as a dendrites, like a hand-like structure. This dendrites is being marked over here, this neuron. So this dendrite is making a connection with another neuron. See, for example, this is another neuron. Okay, the central part is nucleus. This dendrite, it is crossover with another neuron, something like a passing a baton of a relay race. Okay, this neuron is communicating the signal to this neuron using this junction. This junction is mathematically called as a summing point. Summing point. We are forming the summing point in this expression, isn't it? Summing point. What is the summing point? XIW1, or in general, XIWI, X1W1 plus X2W2, and so on, according to the number of inputs what we receive. So biologically, this is called as a synaptic junction. It's being marked over here. According to the strength of the incoming signal, okay, the synaptic junction, the signal may be excitatory or inhibitory in nature. What is meant by excitatory and inhibitory in nature? Because you get a summing point, okay, that mathematically that is being modeled in the form of a threshold function. Earlier, it was modeled it like a hard limit threshold function, but later on, people have arrived at, okay, this is just that nothing like a on and off. Okay, it is giving some partially, it is feeding the information like 80%, 60%, or 10%, 20%. Later on, scientists has understood that. Later on, they converted this hard limit function 0 and 1 as 0 to 1. Okay, earlier they worked like a 0 and 1, either 0 or 1. Later on, they modified this to 0 to 1. Okay, this will be more practical and meaningful because it is a continuous value to be considered as a probability score. Later on, people model this as a probability score. So this is the biological process, receives the sensory inputs, and it is being carried out, it's being communicated via this body. So this body portion is called as an axon. And in axon, it is body portion, you could see there is a covering. Okay, there is a white layer covering. This is called as a myelin sheath. Myelin sheath. Just imagine a semiconductor, a copper wire, how a copper wire carries the current. A flow of electrons, we call it as a current flow, isn't it? Flow of current. Similarly, a flow of signal here, the flow of information. Like how an electrical wire, there is an insulation we have. What is the purpose of insulation? The purpose of insulation is not only as a protection from the shock, it is going to prevent from the losses. Imagine if there is a current flow or electron flow in a copper wire, if there is no plastic insulation, what happens? It is dissipate heat, right? It dissipate heat and there will be signal loss. So you don't get anything, even if you get something, okay, you will get only 20% or 30%. So to communicate the flow of electrons, we have a plastic cladding. Similarly, your neuron also has a myelin sheath as a white, a fat-like structure called as a myelin sheath. Why I'm talking about this is some of the brain-related problems you hear about, mainly related to memory-related issues like Alzheimer's disease, dementia, and all. People, they lost memory, isn't it? You heard about it. We have watched so many movies also inspired by Alzheimer's disease and all. The worst situation is even you cannot recollect the patterns and the activities you have gathered over a period of time. Even you don't recognize your own spouse or parents' face or your daily task. You cannot recollect. Why it has happened? It is literally there is a damage that happened in the myelin sheath. What will happen if there is a damage that happened in the myelin sheath? You will get a loss in signal, right? Your brain will find it difficult to retrieve the information. All the signal will get lost in these damaged neurons portions. Ultimately, it leads to what we call as a white matter loss because it's white in color. In MRI scan, if you see, the brain scan shows white matter and gray matter. People used to call it as a white matter loss, and that is being depicted in the Alzheimer's disease cases. Okay, it's additional information for you. Anyhow, it does not have any direct context to artificial neural network. So to summarize, what are the things, the key points that you should be aware of? The biological neuron compared to the mathematical model, McCulloch-Pitts model. Okay, let me put a tabular column like this. In biological neuron, this is biological neural network. This is artificial neural network. Okay. What is the input in the artificial neural network? Features, right? X1, X2, X3, and so on. Since we are in the course of foundation course, since as long as we are in the foundation course, okay, I'm attached to the context of tabular data only. Okay, your neural network model can see vision, it can listen audio signal and all, that is different. But to treat that kind of data, as I mentioned in the first session, we need a sophisticated layers called convolution layer and so on. Okay, let us not go on to that specialized layers or not. We'll stick on to the tabular data. So your inputs are like features from the tabular data. For the biological neuron, your inputs are nothing but your sensory inputs. Sensory input. Your sensory neuron, vision sensor, auditory sensors, olfactory lobe sensors, taste bus sensors, and touch sensors. Number two, all these inputs are scaled by weights, isn't it? We call it as model parameters, W1, W2, W3. What we call this is scaled by the weights. How this concept of weight has emerged in mathematically, biologically, what happens whenever a neuron carries the signal, right? The signal is being carried with different strength. For example, one neuron carries the signal with a different strength. Another neuron carries the signal with a different strength. Because the piece of information is not picked by one neuron, multiple neurons. Say, for example, my fingertip. In the fingertip, I'm sensing a heat sensation. I'm just touching my fingertip over the surface of hot surface. What happened? My fingertip is receiving the sensation, not one neuron. Hundreds of neurons pick that information. So not hundreds of neurons all of same physical dimension. One neuron length will be larger, another neuron length will be shorter one. Another neuron diameter will be broader, another neuron diameter will be shorter. We know from electrical engineering, basic electrical engineering or basic physics, we know that whenever the current flow in a semiconductor, a copper wire, or what is the relationship is, whenever there is a flow of current, always it offers resistance, right? So resistance is directly proportional to length of the copper wire and inversely proportional to cross section area. The same logic applicable to the neuron also. Neuron also we are treating like a conducting wire. So as I told, each and every neuron length and the cross section changes. Accordingly, whatever the information it carries, it offers some resistance to the flow. So that resistance is a bit complicated to understand. Just to simple logic, we can understand like it offers some kind of a neurotransmitter chemical. That chemical is offering the resistance. Sometimes it will boost the signal. So it is a combination of both electrical as well as a chemical activity in the biological neuron. But mathematically, how do we relate that? So for every input, we give some strength to this x1. Okay, weighting factor to this. Okay, sometimes this value may boost this value, sometimes it will weaken the value, it will scale down the value, or it may scale up the value according to the learning behavior. Okay, sometimes if this value need to be increased, then only a particular loss can be reduced, means this guy has to increase. Sometimes this guy has to decrease, means it has to decrease it so that it can maintain the reduce the loss in the output side. So after discussing this, we are going to shortly enter into the gradient descent logic. Then we are going to analyze this in detail. What is the learning rule, how the weights are being updated, and so on. So now you just analytical comparison. So for the biological neuron, we are considering the weights as neurotransmitters, chemical signal, neurotransmitter. There are so many chemicals are responsible for offering this resistance, like acetylcholine, gamma aminobutyric acid, and so on. And we talked about X, we talked about weights, right? And summing point. What is the summing point in ANN? Summing point is this is the summing point. Okay, mathematical summing point. Whereas in the biological neuron, the summing point is called as a synapse, synaptic junction. So in the summing point, either I can take the output as 1 or 0 on what basis? Based on the threshold. Okay, based on whether the net value crosses the threshold or not. If it crosses the threshold, 1, otherwise 0. Whereas in the biology, we call it as an excitatory state or inhibitory state. What do you mean by excitatory state or inhibitory state? I'll give a practical example. Assume that you are touching some hot surface by mistake. By mistake, you placed your hand on some hot surface. For a few seconds, your brain was not sensing it. For a few seconds. It means what? Your finger, your surface of the hand is picking the data, picking the signal. But certain neurons are communicating the signal as a baton, okay, passing the signal. At one point of time, at one certain connection, the cumulative signal strength is not crossing a threshold. It means what? It goes on inhibitory state. That is why it is not reaching the final your brain. From the sensory neuron, the signal has to communicate to the central nervous system, right? Then it has to take a decision. Hey, it is a hard surface, take the hand out. That is, your brain is commanding to your motor neuron. So your motor neuron, it's taking the hand out immediately. So biologically, what we call, sometimes your signal strength can cross a particular threshold. We call it as an excitatory state, or sometimes it may not cross the threshold, inhibitory state. It will cease out. The signal will dead. It will cease out. Sometimes it will boost. So that is being mathematically, initially it is being modeled as a threshold, crossing a threshold or not crossing a threshold. Later on, this hard limit function is changed to soft limit function as a sigmoidal function or logistic function. So this is a quick comparison between a biological model and the mathematical model. Okay, now we'll see what are all the drawbacks of this McCulloch-Pitts model. Why people are not taking it forward. If you look at the evolution, the first slide, I have marked the evolution. Also, in the previous session, I talked about the winter period, right? Always there is a bust will happen, and immediately that bust will cease down. After there was no talks, that is called a winter period. 4 or 5 years, sometimes a decade of silence. There is no much development happens, and again there is a big breakthrough happens. So 1943 McCulloch-Pitts model, okay, nearly till 1958 there was not a very big breakthrough happens. Okay, some little bit advancement happened. People have introduced a soft limit function. After that, there is no major change in the architecture wise. So the next big change, even in terms of a learning wise, I can say a learning wise, more than a physicality, the learning wise, even in fact, this McCulloch-Pitts model just provide the hardware infrastructure. That's all. They just demonstrate a hard wiring computation system. There is no learning scope. Let us understand why there is no learning scope in McCulloch-Pitts model. Later on in Perceptron, Rosenblatt has introduced a learning scope. He introduced a rule for learning, the weight adjustment rule. This weight adjustment rule has born as a result of gradient descent learning rule. Look at the year 1958 itself, the foundation to the gradient descent concept has emerged, and that is being people have already started adapted that in a linear regressor and a logistic regressor. As I told you, a neural network without hidden layer is equivalently treated as a linear regressor or logistic regressor. So the hidden layer concept is introduced by Widron-Hoff again around 1960. Okay, the full-fledged the learning, how the learning has to be adapted or extended to hidden layer, Geoffrey Hinton has proposed that idea. So the more stable learning idea came to solve a nonlinear problem. Okay, look at the journey from 1943. It reached 1985 to figure out. Until then, around 1960, people were able to solve only linear problems, just like linear regressor and logistic regressor. Only after Geoffrey Hinton demonstrated how we can, if we can extend the same gradient descent logic with the hidden layer, okay, people started solving nonlinear problems also in 1985 onwards. It's popularly called as the backpropagation learning. Okay. So today we are going to, the agenda of today is to demonstrate McCulloch-Pitts model and the earlier stage Perceptron model. In fact, Geoffrey Hinton, Widron-Hoff got the inspiration from a Perceptron model. If there is no Perceptron model, these guys could have not modified that rule. With a little bit modification, people have adapted the Perceptron, single layer Perceptron to multi-layer Perceptron. Okay, it is just an adaptation. But the very major contribution is proposed by Rosenblatt Perceptron. Later on, still Rosenblatt also contributed for the multi-layer Perceptron, but along with Rosenblatt, the new few more scientists has joined hands. One of the significant scientists is Geoffrey Hinton. So now we are going to see these two algorithms, okay, along with the logic behind gradient descent learning. Why McCulloch-Pitts model was not so popular? Again, immediate winter period happened. After 1943, there is next big breakthrough happened in 1958 only. So the middle is the winter period. Winter period in AI research. There is no much development happening. What is the reason is, of course, McCulloch-Pitts, they have provided a hard wiring, physical wiring. But where is the intelligence? Where is the learning? That is not provided at that stage. So by the time from 1943 to 1958, some development that happened in the computers also happening parallel, Fortran and things, computational, scientific computations also happening. So people were able to start demonstrate the learning idea. So what is being considered as a drawback in McCulloch-Pitts model, the initial level McCulloch-Pitts model is human intervention is required to set the threshold value for each problem. If I wanted to solve AND logic, for AND logic, I have to manually tune the voltage value. As I told you, voltage value is the threshold. Say, for example, I set the value is 0.35 millivolts to solve this guy needs. Okay. Why 0.35? It's based on my initial weights. Based on my initial weights. Because we are going to feed two inputs, right? X1 and X2. And for each input, I need to provide weights. These weights does not have intelligence to change according to the input-output relationship. There is no learning. So that means whatever the value you are going to fix, it's fixed. It's a constant value. Since you are fixing a constant value, automatically there is no scope of learning, isn't it? There's no scope. You are not going to change it. It is a fixed. Throughout the process, it is fixed. That is why there is no scope of learning, and weights are same for all inputs. It can be same. You can keep it like a same. Since it is a no scope of learning, it is a constant value. Either you can keep it same or even different. So whatever the value you choose, for example, W1 you choose 0.5 and W2 you are choosing 1.5. Okay. According to your weights, manually people has to adjust the threshold value. The logic is very simple. See here, I wanted to demonstrate AND logic with the fixed value. See, this fixed value it's tuned based on the resistance. You know the resistance. They choose a resistance. For 0.5 they choose a resistance, and for 1.5 they offered a different resistance. Okay, this is 0.5 and this is 1.5. So this is not modified, it's fixed one. Now I need to demonstrate AND logic, right? How can I demonstrate AND logic? X1 and X2 and a net value 0, 0, 0, 1, 1, 0, 1, 1. First, when I plug in the first value, what will happen? 0, 0. 0 times 0.5, 0 times 1.5. What is my net value? 0, isn't it? Next, I present 0, 1. Next, I present 0, 1. 0 times 0.5, 1 times 1.5. What is the net value? I get 1.5. Then 1, 0. Now I present 1, 0. I'll get 0.5 in the output, isn't it? Whenever I present 1, 0, 1, 0, 0.5 plus 0. Stop me at any place if you are not following or if you are missing track. Please stop me.
Yeah, sure.
Whenever I present 1, 1, what is the output? 1 time 0.5, 1 time 1.5, I'll get summing. I'll get 1.5 plus 0.5, which is 2, right? 2. Now the idea is very simple. For the first 3 values, okay, my neural network should not fire, because what is the output? Output is 0. Only if the model reaches the voltage above 1.5, okay, then only I should make the output to glow. They were demonstrated using some lighting bulb. Okay, so easily you can choose a threshold. What is the threshold for this? I can choose a threshold somewhere like 1.75, isn't it? So don't worry about the unit, whether it is a millivolt or microvolt and all. It's all depend upon what is the rating of this resistance they have offered and all. Let us not go to that level. Let us see this as a number only, mere number, because we are not going to demonstrate using a hardware circuitry. We are going to, in modern day, we are going to demonstrate using a Python code. So we'll end up with some number like this. So I will be carefully choose the value between, okay, what is the margin here? 0, 0.5 and 1.5. So the margin lies between 1.5 and 2. So I can choose this very safe threshold 1.75. So I can create a logic. If any value goes above 1.75, I'll consider as 1. Less than or equivalent to this threshold, I'll treat it as, okay. Even if it is equal to that value, I'm going to treat it like this. It has to cross 1.75 and above. So this is simple logic. So what is the problem with this logic is, suppose if I wanted to demonstrate for another logic, what is the another logic? OR logic. For OR logic, okay, any one input is on, okay, my circuit will give output. So my target is something for OR logic is only for 0, 0 pattern, my output is 0, rest all the pattern I should get 1. Suppose you are going to proceed with, okay, if I'm going to proceed with same set of weights, but this threshold will fail to demonstrate OR logic, isn't it? So to demonstrate OR logic, okay, so my inputs are same, my weight also I have not modified the weight, same weights I'm going to use. But this time, if I'm going to demonstrate the OR logic, what is the threshold I should choose? Now, between which interval I need to choose a threshold? It's very clear. Look at this net value 0. Okay, which is the next highest higher value 0.5. So I need to choose between 0 and 0.5. So we can choose 0.25, a safer threshold. If any value above 0.25, my neuron should fire 1. Any value below 0.25, it should not fire 0. So that is the problem with McCulloch-Pitts model. Problem to problem, human intervention is required to set the threshold. You understood why human intervention is required to set the threshold? According to the problem, I need to go and change the threshold. So there is no automation, isn't it? There is no automation. So since there is no automation, there is no scope of learning. So first I will demonstrate this with a simple Python code. Okay, then we'll come back and understand what Rosenblatt came and proposed. Okay, Rosenblatt came after 15 years, nearly 15 years, 1943, and this happened 1958. Yeah, 15 years, nearly 15 years. Rosenblatt allowed the model to learn weights. So by the time after 15 years, slowly the gradient descent logic has emerged, and people started using that logic, and they were applying that logic to adjust the weights. So model possesses some kind of intelligence, learning, automatic learning. So Rosenblatt allowed the model to learn weights rather using the fixed weight, which was early proposed by McCulloch-Pitts. Also, another interesting point is, also Rosenblatt is the first person who introduced the bias. So let me finish this discussion, then I will talk about what is the actual role of the bias, how it is providing additional degree of freedom to the model parameters. Okay. Now I'm going to shift to the Python node. This is being shared with you along with your very first session Zoom link itself. I hope you have downloaded that file and keep it with you. Even I told you to have a look at that code when time permits.
Yeah.
Yeah, look at this portion. Say this piece of code is not for any to solve any practical problem. This is just to really appreciate the mathematics of McCulloch-Pitts model, Perceptron model. Till the back propagation model, to understand the mathematics, we are going to use a contrived data set. What do you mean by contrived data set? It is just a imaginary, a toy data set, just to appreciate the math behind and the logic behind. Okay, towards your session 4 and session 5 only, we are going to the last 4 hours, we are going to work with some realistic data set, tabular data set. Of course, with a challenging data set. Those data sets are challenging for the linear models. The linear models could able to give 60% or 70%. Neural network model is going to demonstrate a 90 and above performance. So that kind of challenging data set we are going to take, and we are going to demonstrate how adding more and more hidden layers, it is going to improvise the performance. Okay. Till first 3 sessions, our focus is on to understand the math. So to understand the math better, we need to work with a small toy data set. There are two possibilities. One way you can choose your own manual weights, or you can choose some randomly selected value. A random.rand function, I choose these two weights as a random weights for me, just to have a different value for me and you guys. So I have commented the random seed. Otherwise, whatever the initial weight value I have got, you will also have the same value. So just I wanted to leave some room for you to fix your own threshold. Okay, I just commented this. Otherwise, if you wanted to have the same value, just uncomment, set some random seed, whatever the value I generate, your value also will be the same. So I should also run, you should also run. So it doesn't matter. Assume that I have started with these weights. Okay, that means my initial weights are like this. So my inputs are two inputs, x1 and x2, 0.54, and this guy is 0.89. Okay, this is the summing point. What we call the summing point output is called net. What is the net over here? X1 W1 plus X2 W2. Since there is no bias introduced, there is no bias. So X1 times 0.54 plus X2 times 0.89. So first I plug in 0, 0. Okay, when I plug in 0, 0, you get net value 0. Next we'll plug in 0, 1. When I plug in 0, 1, my net value is 0.89. Then I plug in 1, 0. My net value is 0.54. Then I plug in 1, 1. Around 1.4. Okay, roughly it's 1.4. So first three pattern belongs to one class. Which class belongs to 0 class? No firing class. Okay, 1, 1 means it should fire 1. So look at this. This is 0, 0.54, 0.89. It clearly indicates that they are linearly separable. Isn't it? Linearly separable. So I can carefully choose a threshold somewhere around 1.0. So all these values are below 1.0. So only this value is crossing above 1. Or you can choose 1 or 1.2 or 1.3, any value. Whichever the value gives the maximum margin, we choose that. So one side of the boundary, you have the upper limit is somewhere close to 0.9, right? And this side you have got 1.4. You can choose some safer margin value. Let me choose around 1.2. Okay, 1.2 or 1.25. So I'm going to choose 1.25 threshold. In similar manner, according to your initial weights, you can choose your threshold. Okay. So I'm going to bring this in the program framework. It's very simple. First, I have to define my pattern 0, 0, 0, 1, 1, 0, 1, 1 along with the target. What is my target? For the first three pattern 0, last pattern 1, right? So I'm defining my data. So this is my data. Look at this is my initial weight. I'm printing my initial weight. See, second time if you run means, see, when you run this for the second time, again, your weights will change. You have to change the threshold. Be careful to run this for only once. Okay, till the time you demonstrate this, you run it for one time and afterwards don't run this set. Now you come here directly. Okay, next step is to define the hard limit activation function, simple threshold based activation function. Just to show you from the programming convenience, I just leave it to you. This is a traditional way. How do you write the function in Python? User defined function. You start with a df keyword. This function is going to receive the net value. You're going to call the function, hey, my ACT, if my net value is 0.7, what is output? The score is below the threshold, isn't it? What is my threshold? My threshold I have set 1.25. 0.75 is below the threshold. My output is, it is going to give 0. Again, I'm going to call the function, hey, my act, I have got some 1.20. Again, it is going to show the output. So this is the user defined function. So it is going to receive the net as the input and it has to take an action. What is an action? If the net value is below certain threshold, it has to return 0, otherwise it has to return 1. So less than 1, automatically the else part is greater than or equal to 1. So this is a conventional way you can write the program. And moreover, look at the function. You have only one simple condition. Suppose if you have a multiple process, maybe this style of function definition could make sense. But simply you are doing only one condition. If the net is below or above certain value, you are making a simple decision. So for single task, okay, instead of writing a traditional function like this, you can write an anonymous function. So anonymous means a nameless function. In Python, this anonymous function, a nameless function, is popularly called as a lambda operator. Using a lambda keyword, okay, so you can write the whole thing as an inline function. There's another name for this, is called as the inline function. Other softwares used to call this as an inline function. Whatever the variable name you are defining, that variable name itself taken as a function name. Look at what is the variable or object name I'm defining in the left hand side. The left hand side, I'm defining an object name called ACT underscore function. This itself is going to act as my variable function name. And then I'm introducing a lambda operator, lambda. In your traditional function, we pass your input argument using a braces. But in the inline function, we don't use braces. Rather, we leave a blank space and then you specify your input variable. See, this is the user defined. You can use any name for it. Okay, not necessarily you should put the net here. It is just a user defined value, or even you can call it like a sum or SOP, sum of products. Any name you can give it. And how do you write this? This is something like a list comprehension in Python. You are familiar with the list comprehension. For val in, we map to a certain range and we give a condition to this val, right? In a traditional for loop. Whereas in the list comprehension, you don't need to write a for loop structure. You can put everything in like this. Val, okay, for val in some range of values, and you can, if at all, if you want to give some conditions, that condition also you can give in a space. Like the same manner, here you're you're defining your inline function like a list comprehension. So how do we write a list comprehension over here? I'm giving you the result first. You should give the result. What should be the result? My result is 0. Okay, under what circumstance? If the net value is below threshold. All I need to change is only the threshold, right? Either you can use a traditional user defined function like this, okay, 1.25 according to this weights, or an inline function like this. If this condition satisfied, it will take the first value. Otherwise, it will take the else value. So it's everything we have done in single line. So just to demonstrate both, okay, I have kept in a 2 different variables. So here my function name is my underscore act. Here my object name is act underscore function. Okay. So whichever the function you wanted to operate, you can operate here. Okay, let me clear all my drawing over here. Okay. So both the functions I have enabled. So I'm run a for loop to access all the records, right? So I'm mapping for X in train data. Why I leave underscore here? Because when you map the train record, I have entered the values like a tuple. The tuple, this is the first field of the tuple. This is second field, right? Whenever you map this kind of data structure in a for loop, you have to pass 2 variables because the first variable will map this guy. Second variable is going to map this guy. So anyhow, I'm not going to do with the target. So I need to feed my input because x1 w1 plus x2 w2 need to happen, isn't it? So what I need to perform over here, I have to perform sum of products, dot product, right? So I'm using dot function here, or even if you wanted to manually operate it, also fine. X star W, you have to do it. Or rather, I'm using this function, dot function. What dot function will do? For the first instance, X will take 0, 0. Okay. W is already a row vector. You could see W is a row vector, 1 by 2 row vector. So sum of products will happen. X1 multiply with the W1. This is X2 multiply with the W2. It's going to produce the net. So I'm printing the first field. What I'm printing? The first field I'm printing the net value. And then f of net is nothing but the net value passing on to the activation. First, I'm passing the inline function, act underscore function. I'm passing the net. Okay, let me run this. 0, 0.89, 0.54, 0.14. This is what we have seen, isn't it? So can you see the output? Whatever the output, 0001. It is simulating McCulloch-Pitts model. We are simulating using a simple Python code. It's very simple and straightforward. As long as you keep the same weights, and if you try for another logic, you have to simply change only the threshold value. Okay, to quickly demonstrate whether this activation function is going to work or not, instead of this lambda operator object, I'm going to pass a traditional user-defined function, my act. What is the name we kept? Yeah, my underscore act. Let me rerun this. This also producing the same. Okay, just a 2 variation, just for your convenience. Whether you, if this approach is comfortable with, you can define like this. Otherwise, you can prefer this. Not a big deal. Now, if I try to perform for OR logic, okay, for the OR logic with the same weights, it won't work, obviously, isn't it? It won't work. Let me comment this weights here. Now I have updated my train data with a different pattern. 0, 111. Can you notice 0, 111? Only for the first pattern, it should fire. We have not modified the weights, isn't it? The fixed weight. If I go, I'm not going to run these two activations, these two cells. Let me proceed with the same activation function. I'm straight away go here and I'm going to this activation function. Let me comment. So here. So I'm not executing this activation function. I'm going to continue with the earlier activation function, earlier threshold, which is designed for AND logic. Okay, now I'm going to run this. What we are supposed to get? 0, 111 we are supposed to get, right? How your model is working? Anything above 1.25, it is going to fire. But look at this, these guys are below 1.25. This is also below 1.25. That's why it's not firing. But as per OR logic, okay, if any one input is on, output should fire. If at all, if output should fire, I should lower the threshold value, isn't it? I should lower the threshold. So the same threshold will not work for a different problem. So human intervention is needed according to problem, different problem. That is why there is no autonomous. There is no learning scope. So what we need to do, according to the problem, we need to change the threshold. So now I'm going to modify the threshold. Let us keep 0.25. Okay, 0.25. So let me update act underscore function. So now the act underscore function is updated according to the OR problem. Okay, and then I'm going to read this. We got 0, 111. As long as weight is fixed, you can go ahead with this threshold. Now, the moment you change the weights, okay, everything will change. Look at here. Now I'm going to rerun this. I'm going to rerun this. This time it is going to take a different weights. Different weight because my resistance changes. As my resistance changes, it is offering a different resistance to the flow of the input. So the same threshold will not work. Look at this. So for the updated, for the different set of initial weights, I am going to check this once again. My act, let me try this my act. What is showing? Our earlier threshold was 1.25, but look at the net value now because of the change in the resistance. For the first three value, it should produce 0. For last value, it should produce output 1. What is our threshold? 1.25. Even this net also fall below 1.25. So model could not fire it. So I need to lower the threshold according to the change in resistance, change in weight. So any value above 0.65, between 0.65 and 0.70 could be fine. 0.68, right? Let me choose 0.68. I'm choosing 0.68. Now it will work. Either use this function or this function. Okay. So let me use my act here. So I updated the threshold. This time I will get 0.01. So this is the simple and straightforward logic of convergence. Okay. Now we are going to see what Rosenblatt has proposed. As I mentioned, Rosenblatt has proposed a learning rule. Okay. So to understand the learning rule, we have to visit our gradient descent.